Okay, hey folks, I just wanted to give a very brief lecture on electronic circular dichroism. This is mostly of interest to biochemists, but there's a lot of really cool physical chemistry that you can do with circular dichroism, as well as some really cool synthesis stuff. And through synthesis is involving chiral molecules. Okay, so you might have noticed I've got these lovely simulations going on right here next to me, and they're kind of slow running, so let's let them catch up and play. So if you recall, light is an oscillating electromagnetic field that propagates in a certain direction. When that electric field oscillates about its propagation length, then it has become circularly polarized. So let's take a look at some of these pictures so we can see what that is showing. So here the blue vector shows our overall component, where now we might have a 90 degrees phase shift in one beam of light relative to another, which creates circular polarization. So this is most easy to understand if we consider the superposition of left circular polarized light and right circular polarized light. So you might notice that this is just plain polarized. So anytime we have plain polarized light, so one beam of light coming in at a specified angle, it already is a superposition of left and right circular polarized light given by this diagram. So to make LCPL or RCPL, we first start with plain polarized light, and we slow down one of those components by 90 degrees, which creates this delay and thus makes circular polarization through constructive and destructive interference. And so depending on the way that we delay our plane polarized, either to the left or the right, will generate left circular polarized light or right circular polarized light. So this is typically done with a quarter wave plate. So in other words, we would have our plane polarized light coming in, and relative to that beam, so if this is 90 degrees to the beam, we would put a 45 degree like little slit like that, and then going through that slit as it passes through, it creates this interference which makes circular polarized light. So now as you imagine, if we shot plane polarized light into an optically active chiral medium, that medium will interact with one-handedness of the light preferentially over the other, which creates what we call ellipticity. So for example, this is like a cross-sectional view of our plane polarized light before it goes into our optically active chiral medium, and this is a cross-section after it comes back out. And you can see it has this elliptical shape. So we refer to that as ellipticity. So revisiting the Beer-Lambert law, we can draft up the absorbance of left-handed light with the following equation: AL equals A to L, C times L. Right, where we remember that is our molar absorptivity coefficient. And concentration and path length have their normal meaning. Excuse me. We could also talk about the absorbance of our right-handed light in the following way. And now the molar circular dichroism is given by delta epsilon, specifically epsilon L minus epsilon R, or relating that to the Beer-Lambert law, AL minus AR over concentration times path length. So in other words, if a molecule based on its chirality prefers to absorb left-handed light over right-handed light, we'll see a positive delta epsilon. And if due to the structure of our molecule, it prefers to absorb right-handed light over left-handed light, it'll have a negative delta epsilon. So we also commonly see molar circular dichroism expressed in units of molar ellipticity, which is commonly given in degrees centimeter squared per decamole. So the way that we express that, that ellipticity is expressed as this angle theta, and there's a whole bunch of these conversion factors. 180 over pi takes it from degrees to radians. ln of 10 divided by 4 changes our base from base 10 to base e, and a number of other things that go on in there. I'm not showing the derivation of this. So it's routine to see this equation in circular dichroism. So all of these constants end up being 3,298.2. The 100 gets us into the decamole unit. So again, it's common to see this weird number in circular dichroism. So let's take a look at a spectra. So here I have two enantiomers of the tryptophan amino acid, L-tryptophan and D-tryptophan, and the corresponding CD spectra. And now more commonly, these are referred to ECD, electronic circular dichroism. And one thing to note here, this DL-trip, so that would be if we had a racemic mixture. I'm going to draw that in green so we see the connection there. So that green spectra would be racemic. So in other words, there's a 50-50 ratio of D to L. And in this technique, the spectrometer is pulsing left and right circular polarized light with this oscillating quarter wave plate. And the detector keeps track of when is left polarized light hitting the detector, when is right polarized light hitting the detector, and then returns that to be processed. So in a racemic mixture, there will be equal amounts of absorption of left circular polarized light and right circular polarized light, so we don't see any ellipticity at all. So that's why we see 0 ellipticity given here in millidegrees. However, if we have an enantiomeric excess or even just a pure enantiomer, we would see the following. So for example, in D-tryptophan, this feature out here at 200 nanometers is preferentially absorbing left-handed light over right-handed light, right? Because it's a positive delta epsilon value. However, in the opposite enantiomer, we would see a mirror image corresponding to just that. So in other words, in L-tryptophan, this feature at 200 nanometers is preferentially absorbed by right-handed circular polarized light over left-handed circular polarized light. And then similarly, as we continue down the spectra, there's another feature here at 220 where the L enantiomer preferentially absorbs left-handed light and thus has a positive peak, and the D preferentially absorbs right-handed light and has a negative peak. And it doesn't have to necessarily equate that like all L enantiomers will preferentially absorb left-handed light. This depends on the structure, it depends on the transition in question, whether it's pi to pi star or N to pi star, for example. And looking at this molecule, hopefully we can gather these features are related to pi star transitions due to where they occur in the spectra around 200 nanometer. So we can use this as a diagnostic to work out if a molecule has chirality or even what an enantiomeric excess might be if we have a mixture that's not quite racemic. Okay, so that's all that I'm going to say about ECD. So we could go into all kinds of complications, like actually trying to interpret what features we might expect to absorb left-handed light over right-handed light, and so forth. I don't want to get into that. I just wanted to talk briefly about the technique. Okay, folks, I'll see you in the next video.